In the last video, we took a look at centripetal acceleration, came up with the fact that if an object is moving in a circle at a constant speed, then it is accelerating toward the center of that circle at v squared over r. Here now I'd like to go ahead and introduce Newton's law of universal gravitation. So when he was thinking about gravity, he had the realization that the force that makes apples fall at the surface of the Earth is also the force that makes planets move in the heavens. Thus the notion universal, which was a big deal because there was still some holdover of Aristotelian thought that somehow the laws of nature had to be different in the heavens than on the Earth. And Newton was able to find at least one law of motion where that wasn't true. In his analysis, he eventually worked out that the force of gravity had to go directly as the mass of the two objects and inversely as the square of their separation. This constant proportionality is the universal gravitational constant. It's approximately 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now, this is for 2-point masses. If you have objects of extended size, invoking a thing called the shell theorem, what you can do is you can show that you can treat them as if they were point masses located at their center of mass for purposes of calculating this gravitational attraction. And it is always attractive, and it's mutually attractive. The two masses will always exert the same force on each other, no matter what. So how does this tie into the mg that we saw before? Well, okay, let's just say you're standing on the surface of the Earth here, like so. So here's the radius of the Earth. We can say that the force of gravity on you would be equal to big G times the mass of the Earth times your mass over r squared, where r is the distance from your center to the center of the Earth. But your center is roughly a meter above the surface of the Earth. So the difference between the distance center on center from you to the center of the Earth versus just plain the radius of the Earth is the same to literally 6 figures. So you can just put in the radius of the Earth squared. Now, if you multiply and divide all these numbers through, you will get 9.8 newtons per kilogram. So we just say that all of that is our little g, and that gets us our mg from before. And you can do this, nothing says you have to do it at the radius of the Earth. If you want to do this at the altitude of the at the height of the International Space Station, you just put in the radius of the International Space Station's orbit. You'll get 8.9. If you want to do this on the moon, well, you'll have to replace the mass of the Earth with the mass of the moon. You'll have to replace the radius of the Earth with the radius of the moon, and then you'll get a number that's about a sixth of that. So we'd already argued that if something is in orbit, it's because it's falling around it. So this is what allowed Newton to tie in with some empirical observation by Johannes Kepler. Kepler had taken a look at the motion of planets around the sun, and one of the things he worked out was that the orbital period of a planet around the sun, if you squared that period, the square of that period goes as the cube of the orbital radius. And that's supposed to be a circle-ish, but that didn't work out too good. So this is Kepler's third law, also known as his harmonic law. It says that t squared is proportional to r cubed. So let's go and figure that out. Well, the only force acting on the planet is gravity. So we can say that the gravitational force is equal to ma. And then we can put in what these are. So the gravitational force would be big G, mass of the sun, mass of the planet, over r squared, mass of the planet. And then since it's going in a circle, we can say that that's v squared over, just over r. Cancel, 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 cancel. Okay, but the speed would be 2 pi r, that would be the circumference, over the period. So let's put that in. So we'll have to gm over r equals 2 pi r over the period squared. If we work that through, we get that gm over r is 4 pi squared r squared over period squared. Do a little bit of cross multiplying action to match how Kepler wrote it. You get t squared is 4 pi squared over gm times r cubed. So Newton was able to show that Kepler's empirical data fit worked by showing that that was a result of gravity doing its thing for an object in circular motion. Now, I swept some details under the rug. In reality, planets move in ellipses, most of which look almost very close to circles, but it does make the math a lot more tedious, but you get the same result. And the other thing is that I've assumed that the sun stays totally fixed down, which isn't quite true. A more careful analysis would show that instead of just having the mass of the sun in the denominator, it would be the combined mass of the sun and the planet. But in the case of weighing the sun, that would be like the difference between weighing a dog with or without its fleas. So to many digits, you'll get the same answer either way. Now you can use this same trick for measuring the mass of planets. And again, you can usually neglect the mass of the moon that you would use looking, whose orbital characteristics you're using to deduce the mass of a planet. But there are two exceptions in the solar system. One of them is the Pluto-Charon system. The mass of Charon, Pluto's moon, is a substantial chunk of Pluto. And the Earth-Moon system, it turns out that the mass of our moon is a substantial chunk of our own, a few percent, enough to throw the answers off. In that case there, what you have to do is you have to solve for the combined mass, and then you have to carefully measure where exactly the Earth and Moon, the common point about which the Earth and Moon are orbiting about, and split that off like a teeter-totter. But most of the time you don't have to care about those things. So let's just go and take a look at how you weigh a planet. So for instance, if we look at the mass of Saturn, if you want to know the mass of Saturn, what you could do is you could look at its moon Titan. Now it has an orbital period of 15.945 days and an orbital radius of 1,211,850 kilometers, both of which have been determined quite accurately by telescopic observation. That's enough to figure out what the mass of Saturn is, because we can invert this around. We get that the mass would be 4 pi squared r cubed over gt squared. So this will be 4 pi squared, and then you'll have to take your kilometers, make them into meters, so 1,211,850,000 meters cubed. over 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then same deal here, you're going to have to take your days and turn them into seconds. So you're going to take your 15.945 days. 1 day has 24 hours. 1 hour has 3,600 seconds. Cancel, 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 cancel. And you're going to have to square that. So anyway, when you crank the values through, you will indeed get the mass of Saturn. Alrighty, so with that one, I will catch you all in the next one. Have a good day.